Okay. It's 1 minute to 6, so let's just start. Hello, everyone. Good evening, and welcome to the problem solving session of Data Science for Engineers NPTEL course. And this is week 4. And I am your TA. My name is Saladi Pravalika. I'm a BMRF and also a PhD scholar from Indian Institute of Science, Bangalore. And before I say something, um, session is being recorded. Okay, and I will give you 3 to 5 minutes break every half an hour and 10 minutes break every hour. And if you would like me to cover any more topics in the next sessions, please let me know. And also, please be respectful. And I will not hesitate to remove you from the session if you are not being respectful, either to me or to any other participant in the chat box. Okay. Yeah. Good evening, everyone. So let's get started. Uh, so basically, some of you had this particular doubt, like why are we learning about linear algebra or the statistics? Like last week we were covering about mean, mode, and all of that, and before that we were looking at eigenvectors, eigenvalues, which is like linear algebra. And this week we are covering optimization. So many of you were asking, like, why exactly are we using learning these when we have signed up for data science? So these three are basically like the three pillars of data science, which you can see here. So I have taken this image from Geeks for Geeks. Yeah. Okay. So for today's topic, we'll be discussing about optimization. So optimization of univariate optimization and multivariable optimization. Also, we'll be looking at gradient descent as well, right? So what exactly is optimization? Like, where do we see it every day in life? Any examples that you can give, except for the one which is already here? Any examples that anyone want to share? How do you optimize a situation which you are in, like in your daily life, anywhere? Yeah, traveling. Except anything that is related to maps. If you'd like to give anything else. Construction. Yeah, that's a very good example. Thank you so much. Yeah. Well, so I just wanted to take this example of maps. So since many of you use Google Maps when you're traveling, or if you're looking at, if you're going in a bus and if you're seeing the maps and all, so many of you would have used Google Maps at one point or the other, right? So in this, if I am starting from one location, let us say I am in IIC Bangalore and I want to go, let us say to Cubbon Park. Okay, Cubbon Park is in Bangalore. So if I want to go from there to there, from one location to another location, it will show me some distance. Okay. And it will tell me the estimated time it will take for me to travel from point A to point B. Right. Also, it is also going to recommend me some alternative routes. And when I click on that alternative routes, it will also tell me the distance and it will also tell me the time taken. And it might give me multiple such ways, like paths to go from location A to location B. So similarly, as you can see here, so I want to go from point A to point B, right? And Google Maps was showing me that to go from point A to point B, it is taking 6 kilometers. And hypothetically, okay, this is not possible, but like if it is free, it's possible. But yeah, from to cover 6 kilometers, it is taking me 9 minutes. This is a hypothetical situation. I just gave some random numbers there. Okay, and that is path A. And if I take path B, it is taking 5 kilometers, and it is taking me 10 minutes to travel 5 kilometers. It may be because of the presence of traffic or etc. 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 Right? And if I'm going from point A to point B in the path of C, it is 9 kilometers and it is taking me 13 minutes. Right. So if you look closely, uh, route A is going to take the least time of all. Right. So if I want to be time efficient, if I want to optimize my path with respect to time, then I can prefer route A. So route A is optimal time path. Okay. If at all you are looking at distances, you can look at path B, which is 5 kilometers. So if I want to optimize from going from point A to point B in 5 kilometer, like in less distance covering. But even though I don't have a problem if it is going to take me a minute extra, then I will take point B, and that is my optimal distance path. And if you are looking at C, it's like it's the distance is also more, the time is also more. So it is just another route. It is not an optimal route that we are going to take, but rather it is just a normal route and okay. So C is the other. So optimization. So the definition of optimization is use of a specific method to determine the best possible solution. So as we were looking at in this example, A to B, then we are analyzing how much time it is going to take, how much distance it is going to take. Based on that and the situation that we are in, we are going to estimate them, like we are going to have different methods. So for example, if I want to take less time, I will look at all the time taken for all the three paths. If I want less distance, I will look at the distances between point A to point B through via these routes, right? So I am doing some kind of optimization, so that is a method that I am following. So that method is nothing but optimization, right? So here are two examples. Sorry. So let me say that I have two variables x and y. Okay, and I have some values that x and y are going to give. Let me say I'm having some equation like z is equal to 2y plus x or something. Okay, and with for different values of x and y, I'm going to get different values of z, and I have plotted everything in one place. Okay, so now if I see, I have drawn or I have already pointed all of these lines. Okay, this is not exactly right. Okay, so I have marked some points here and there. And then I am going to draw a line that is going to fit the data such a way that the distance between the point and the line that I'm drawing is minimal as possible, right? I can have multiple other lines as well. Let us say if I'm drawing like this, or maybe like this, right? Um, okay, like this and this. Then I might get different values for the distances between these points and the lines. Okay. Uh, so now within the like among these three, I have to find which one is the right one, like the closest possible to all the points in this. Okay. So this one particular line might be my most optimized path. Okay. Uh, just a second. Someone is asking some questions. Um, Only on the third week. Solutions are not being shared for the past week assignments. I'm really not sure about why the solutions are not being shared. I can bring it up with the NPTEL team. Okay. I am not the right person to answer any of that. Okay. Also, particular. I have a doubt on a problem. Can you help me solve that? Yes, I can help you solve that, but after the end of this session. Okay. Yeah. Also, if you are sending a message in the chat box during some session, please make sure that it is relevant to that section. But at the end, I will certainly ask everyone which questions you have, and at the end, you can definitely ask your questions which are not relevant. Okay. I mean, not relevant at this point. Okay. Yeah. So, okay, sorry. I'll just use black. Okay. Yeah. So let me just let us see another example. So these red marks are of data A. Let us say they are called data A, and let us say these green marks are data B. Okay, and I have pointed them here and there. Okay, so I have them, And now I am trying to divide both the points that belong to data A and data B. Okay, so I need a line such a way that I am that I'm dividing the data in such a way that it is being grouped according to the similarity that it has with the other data. So all these red points are one type of data. All these green points are another type of data, right? If I draw a line here, then I am grouping these separately, even though I have one red in green, but still I am able to cluster it. The remaining ones are being clustered properly. Okay, so this is my most optimized line which I can find, right? So before we go into multivariate optimization problems, we can just start with a simple univariate optimization problem. So univariate means one variable optimization problem. So in this one, we just have only one variable to focus on. For example, x or y or z. Just one variable we are going to have. So we represent the uni optimization variable in this way. Here, in this way, we are going to write. And the main components are an objective function. So this f of x is the objective function, okay, and a decision variable. So what kind of decision we are going to make is going to be based on one single variable here. So that is this univariate variable, which is x in this case, okay. And also we have certain set of constraints. Okay, it can be x lies between 1 and 2, x lies between minus infinity to plus infinity. There are some certain constraints that we are also given, and that constraint is this here for us. Okay, that x belongs to R, right? So far clear? Yeah, thank you. Yeah. Then we'll look at four topics here: global maxima, global minima, local maxima, local minima, right? I have this graph. Okay, I am naming the variable. Okay, it is not much clear. Okay, I'm marking points, some points here. Okay, let me say this is 1, this is 2, this is 3, and this is 4, and this is 5. What do you think the global maxima is? You can just give the number there. Awesome. Thank you, guys. Yes, 2 is the global maximum. Okay, so global maxima means the maximum value that you are going to find in the entire path of it. So my entire path is starting from 1 to 5. I'm having everything. I'm considering all the x values. And then I'm plotting something. And then I'm getting the highest at 2. And that is my global maximum. And global minima is at where? At which point? C. Yes. So global minima is at 3. So global minimum means I'm taking the entire path and then I'm finding the minimum value out of everything, right? And whereas if I'm taking, uh, let us say, this is x1 to x2, and I'm only considering this path from here to here, only these x values. Okay. Then what is my local maxima? Exactly. Right. So local maxima is if I'm giving a constraint, I'm looking at only one part of the entire path and I'm finding the maximum value there, right? And what do you think of local minima? Absolutely. So this is between x1, x2. Okay. Hmm. So you got this, right? Anyone has any questions here? Good. Um, I just explained both here. Okay. So now we are finding I have given this entire graph so you are able to figure out where is what and all. So let us say I'm giving you one complicated f of x value, some function I'm giving like really complicated, then it is not possible for you to draw a path, I mean, or a graph like this and then figure out which point is where, right? So instead, what we do is we look for some conditions for x value to be a minimizer. So x value to be minimizer means the point where x is the least for us, okay, or maximum. So the condition is f dash of x is equal to 0. So you are going to differentiate f of x with x so that, and then you equate it to 0, and then you get the x values, right? Okay. So that is a necessary condition. There are two types of conditions. One is necessary condition, one is sufficient condition. So this is the first condition. So this f dash of x equal to 0 will give you some critical points, the point at which it is maximum or minimum, right? And then we look at sufficient condition, which is f double dash x is greater than 0. F double dash means you are going to differentiate f of x twice. I hope all of you know differentiation. Okay, so I'm not covering that part. Okay, so example I'm taking here one f of x value, f of x function, x sine x square plus 1, right? Sorry. So I'm taking the graph here and then we plot the graph. I'm plotting the graph as well. And then you can see where the global maxima, global minima, and all of that is. Okay, and this a is equal to minus 2 comma 2 comma 2.51 is nothing but a condition. Okay, I want to look from this point to just this point, right? Just like how we have seen for local maxima and local minima. Okay, and then we try to figure it out. Okay, let's do one example so that it will be clear. You guys want to try, or do you want me to explain one and then you want to try the other ones by yourself? Um, you want me to explain or not connected still? Yeah, okay. Yeah, I'll explain. 1 second. Okay. Sorry. So let us write f of x first again. Is x square. And f dash of x is equal to, the 4 comes in the front and the degree reduces by 1 minus 3 into x square by 3 minus 2x. 3 and 4 gets cancelled. And then we have x cube minus x square minus 2x, right? So according to the necessary condition that we have, we need to equate f dash of x is equal to 0. Okay. So I'm writing this is equal to 0. I'm taking x common. So x square minus x minus 2 is equal to 0. So I have an option, either x is equal to 0 or x square minus x minus 2 is equal to 0. Okay. I'll write this as x square minus 2x plus x minus 2 equal to 0. X minus 2 into x plus 1 equal to 0. So I have x equal to minus 1, 2, right? And we also have x equal to 0 here, right? So all the possible values are minus 1, 0, and 2. Got it? So these are my stationary values. Okay. So we are given f of x and we are asked to find stationary points. Stationary points are nothing but these x values that we are supposed to find. Right? So I have taken f dash of x equal to 0. The first order of f of x is equal to 0. And then solving that equation, it gives us the stationary points. And the stationary points are -1, 0, and +2. Right? And then let's go to the second order condition, which is minimize double dash of x is greater than 0. Right? But mm, is it clear so far? Yeah. Thanks. Okay. Mm. So let me write f dash of x here again. X cube minus x squared minus 2x. Okay. Now let's take f double dash of x, which is 3x squared minus 2x minus 2. Right? So now I'm going to put the stationary values in the above equation. Put stationary values in the above equation. That is f double dash of x. Right? So my x values are -1, 0, and 2. F double dash of -1 is equal to 3 minus 1 square minus 2 minus 1 and minus 2, which is equal to 3 into 1 minus into minus is plus 3 plus 2 minus 2, which is equal to 3. Right? And then F double dash of 0. 3 of 0 minus 2 of 0 minus 2, which is equal to minus 2. And then F double dash of 2. 3 into 2 square minus 2 into 2 minus 2. 3 into 4 minus 4 minus 2. 12 minus 6, which is equal to 6. Am I right? Okay. Okay. So according to the condition, what we should have is f double dash of x should be greater than 0. Right? We are getting this minus 2. So which we are not going to consider. Right? So now we have -1 and 2. Both of them we have. So which one is the value at which the minima exists? Then what we do is we go for the highest value. So this f double dash of -1 is 3 and f double dash of 2 is 6. Right? Since this is the highest value, we say that minima exists at +2. Uh, x equal to +2. Okay. Let's look at the question once. Okay. Okay. And but the problem here is it is asking us the value of x at which the minima exists. So we are not going to stop only at this point. What we have to do is we have to substitute x equal to +2 in f of x. Okay. Submit substitute it in f of x, and then you will get some value, and that is going to be your final answer. Okay, is it clear? The highest value we are taking. So there, we are taking this f double dash of 2 because we have both of these to be greater than 0, right? Then both are going to be the minimum value for us, but the highest value whichever it is giving is going to be the most minimum value, like the maximum global minima for us. Okay, when maximum or minima doesn't exist, yeah, we just write that it does not exist, that's it. Okay, when okay, so I would like you guys to try this one out. Okay, but I'm telling you, do not just simply substitute the values in that and get the answers. Try. Okay, what is the condition? Condition is that f double dash of x is less than 0, less than or equal to 0. This condition will go false for this condition as well. If f dash of x is not equal to 0, then it is not having global maximum, global min, or maximum or minimum. Okay, these two conditions must be solved at no matter what. I'm sorry, I changed this. Yeah, please try to solve this. I'll explain it as well. I'm just giving 2 minutes. Okay, by 6:29, I'll start. Okay, one person is saying A. Any other answers? A. Awesome. Okay. Yeah, sufficient number of people have answered. Amazing, guys. Thank you for your responses. Okay, so let's try it. Try it out. I'm taking f dash of x is equal to 2x minus 4, right? If I'm, yeah, now I should equate it to 0. So 2x minus 4 equal to 0. 2x is equal to 4 and x is equal to 2, right? So let's look at ABC values here. So we are having x equal to 2 here and here as well. Okay. So we are eliminating B and D, right? Now then the other one is f of x. Now let's put this value in f of x. F of 2 is equal to 2 square minus 4 into 2 plus 5, 4 minus 8 plus 5, minus 4 plus 5, which is equal to 1. F of 2 is equal to 1. Right? So the only right answer is A. Okay? Clear on this? Yeah. Okay. Cool. Let's get to our next question. Okay. So this is a bit tricky, but I think you all can do it. But if you're not able to, anyways, I will explain it at the end. Okay. We have some possible rectangles, and the area is constant here. So the area is equal to 100. Okay. And which of the possible which rectangle of all the possible rectangles have the smallest perimeter? Is the question clear? We have so many number of rectangles, and the area of all those rectangles is equal to 100 only. But only one rectangle has the smallest perimeter out of all the possible rectangles. Which rectangle it might be? I mean, the length and the breadth values, what exactly it might be. If the question is not clear, I can explain again. So just drop a message if you are not able to understand the question. The hints are area is equal to L cross B, and L being the length and B being the breadth, and perimeter is equal to 2L plus 2B. I'll wait till 6:33. 40. Okay. Okay. Yeah. Right. Okay. Shall I explain? Okay. Before I begin that, yeah, 40 is the right answer. Okay. So let me just start with it. So let L be the length and B be the breadth of the rectangle. And it is already given that A is equal to 100, right? So we already write L into B is equal to A. So we have to convert the entire, and yeah, the perimeter is 2L plus 2B, right? So now here I'm having two different variables. I don't want two different variables. I just want only one. So let us say I just want B, I mean L. So B is equal to A by L, right? Substitute this one in this. So 2L plus 2 times A by L, right? Which is equal to 2L plus 2 into 100 by L. 2L plus 200 by L, right? And if at all I call that as f of x, first we should differentiate f of x, and then we'll get 2 times minus 200 by L square. Am I right? and this should be equal to 0. So 200 by L square is equal to 2. So L square is equal to 200 by 2, that is equal to 100. So L is equal to plus 10 or minus 10. Since L cannot be negative, we say L is equal to plus 10, right? So what you have got is right, but then we are looking at the perimeter, right? So B is equal to A by L. A is already 100. Sorry, not A. Yeah. Oh, okay. B is equal to A by L. So this is equal to 10. So the perimeter is equal to 2L plus 2B. That is equal to 2 into 10 plus 2 into 10 is equal to 40. Right? Is it clear? Yeah. So if you guys wish, you can take a break for 5 minutes. Okay. And if you don't want to take a break, you can try this question out by yourself. And after this, I will show you our code, our studio in a code in our studio. Please be back by 6:40. I'll start back again in 4 minutes. Yeah. So let us continue. Okay. So now I'm showing you an R code. Okay. At the end, this will be shared on the drive link and you can access it through the drive, right? Okay. So now we are trying to calculate the gradient of a given function. So gradient here is nothing but the f dash of x, right? So now we are trying to calculate the gradient of the of a function using different functions like deriv and d. So there are two types of functions which we can use to take the derivation of the get the derivation of the given function. Okay, so I'm just taking this as an example. Okay, x squared plus 5x plus 1. Okay, again I'll repeat x squared plus 5x plus 1. Okay, so first I'm running that. So that is done. And then cat. Cat here is nothing but like the print function. I'm just printing one complete string. Okay. So for that I'll use cat. And then I'm printing deriv of x of f comma and the variable which we want it to be derivated with, right? So we are giving the function and then with what for what variable we are using for the derivation. Okay. So I'm using this deriv function and then I got this expression. So here what I can see is I have the value x squared plus 5x plus 1, right? And then I have this gradient of x, which is f dash of x, which is nothing but 2x plus 5. Agreed with me? Okay. So I'm getting the derivation of this. But there is another way also to use instead of deriv function, which is just using capital D, right? So f prime is nothing but f dash. I'm storing that in f prime variable. So d of function comma x. Okay. I have stored it in that variable and I'm printing it. And then I'll get the exact different first order differentiation of f of x, right? Okay. So I got that. So if I want to get the second order differentiation, what I can do is I can again differentiate directly this f prime, right? So the second order derivative using the function is print of d of f prime comma x, and that is nothing but 2. Is this one clear? Is this clear? Okay, cool. Uh, okay, so you can try out for different expressions using this code. Okay, I think I have already uploaded this file on Drive, so you can have a look at it also, and you can parallelly do it along with me if you can do. You want me to explain it again? Yeah, sure. So I have this function x squared plus 5x plus 1. Okay. Now I want to get the first order differentiation, that is f dash of x, or we also call it f prime. There are two methods to get f dash of x. One is using this deriv function, another one is using d function. Okay, both are going to give me f dash of x only. Okay, so this x square plus 5x plus 1, this function is stored in a variable called f. Okay, and here I'm showing you how to get f dash of x using deriv function. It is nothing but you'll write deriv, open bracket, the function variable, that is f here. And since we are differentiating it with respect to x, I'm giving x here. Okay. And then I'll print the value. This is my original function, x squared plus 5x plus 1. And yeah, this is my differentiated function, the f dash of x. So 2x plus 5. Okay. So that is using deriv function. But if I don't want to use deriv function, I can also alternatively use d function. So I'm saying assigning a variable f prime is equal to d of the function f, comma, with respect to x, we are going to differentiate it. So I'm giving x, right? And then I'm going to print the value. So directly I am getting f dash of x here. Okay, so that is for the first order differentiation, that is f dash of x. But if I want to do f double dash of x, then what I have to do? I have to differentiate f dash of x, right? So that is what I'm doing here. I'm taking d of f prime instead of f, so that it is going to be a second order difference, second order differentiation, f prime, comma, and x. And then I will get the differentiation of 2x plus 5, which is 2. Is it clear now? Cat function. Cat function is not, you just have to print it. So this slash n is nothing but you are asking it to go to the new line. Okay. So without that slash n, it will be printing in the same line. I'm just keeping a slash in so that it will skip a line and it will go to the next line. Okay. So cat is nothing but like the print function only. So in place of print, you are writing cat and then double column, double quotes, and then slash n is new line. And then I will write whatever I want to print. It's only for string, okay, or a character. You can, whatever you want to print, you can write there. And then I'm again ending it with slash n so that it will go to the new line. Okay. Yeah, done. So hopefully this univariate optimization is clear. We will look at some more examples. Some people have actually asked for more examples to be taught, so I'm focusing more on examples part. All right. So let's go back to examples again. So, yeah. Okay. We will look at this question. So again, some a rectangle problem. So this time we know the perimeter of the rectangle. So 2L plus 2B is equal to 24. And now I want maximum area. Do you guys want to try or should I do? Option A is you guys do. Option B is I do. So if you guys are doing, I'll give some time, but still again I'll explain it again. Okay. Uh, do it. Try. Let's take 2 minutes. 6 till 6:50. I'll wait, and at 6:50 I'll start it back. Okay, lovely people. Option A is absolutely right. So if you did not get it, I will explain it. So we already know the perimeter is this. Okay, I'll rewrite it as L plus B is equal to 12, right? So let us say if I'm taking L is equal to 12 minus B plus 1 and area is equal to L cross B. So in place of L, I'm going to substitute it. 12 minus b into b, which is 12b minus b square, right? So in order to get maximum or minimum value, I have to first differentiate it. So a dash is equal to 12b sorry, 12 minus 2b is equal to 0. So I'm getting b is equal to 6, right? So now I'll take this value and I'll substitute in this 12 minus 6, which is equal to L is equal to 6, right? So we are getting length is equal to 6 and width is equal to 6, and this is the right answer. Cool. Okay. Another question. Uh, we have this function f of x is equal to x cube minus 6x squared plus 9x plus 2. And what are the critical points? So critical points are x values once you differentiate it. Okay. You can try this one. I'll give you like 2 minutes again. You can try this and tell me which one is the answer. Absolutely no substituting the x values in the function and giving me the answers. You have to do it by yourself. Take f of x, differentiate it, and then get the x values. If anyone is not clear on that, you can tell me, and after 2 minutes, I will explain it again. D- D- Awesome. Yes, so D is the right answer. Well done, guys. So once again, if anyone did not get, I'm explaining it. So f dash of x is equal to 3x square minus 12x plus 9, right? I have to equate it to 0. Let's take 3 common. X square minus 4x plus 3 is equal to 0. So x square minus 3x minus x plus 3 is equal to 0. X minus 3 into x minus 1 is equal to 0, and x is equal to 1 comma 3. Okay, so option D is the right answer for this. Simple, right? Okay. Um, you can try this one. So company wants to maximize its profit P, and the profit is a function P of x is equal to minus 2x square plus 40x plus 100. Okay. So where x is the quality of the product sold. Okay. What is the optimal quantity of product to sell? How much quantity do we need for the product to sell? Sorry, this is quality. How much quality of the product is needed for the products to be sold? Oh, you guys are fast. Okay, cool. Uh, shall we do? And yeah, 10 and option B is the right answer. So f dash of x is equal to minus 4x plus 40 is equal to 0. So x is equal to 10. Amazing, guys. So yeah, so this one will be the last question in univariate optimization. So you can try this. And meanwhile, if any one of you are still having question in univariate problems, you I hope you pay attention to this particular problem at least so that you will understand univariate optimization problems better. Okay, this one is the last one that I'm going to discuss in this particular topic. Yeah, okay, we'll continue. Yes, guys, both of you are right. D is the right answer. But we'll see how we have to do. Okay, S dash of t is equal to 40 plus 3 equal to 0. T is equal to, sorry. Oh, okay. My, sorry. Okay, so velocity is nothing but the derivative of distance, right? Since we are given the distance as s of t, then velocity is nothing but s dash of t, right? So s dash of t is equal to 4t plus 3. And since they are asking at t is equal to 2, s dash of 2 is equal to 4 into 2 plus 3, which is 8 plus 3, which is equal to 11 meter per second. Okay. Can we substitute t at this point? At which point? Um, okay. You have asked a question. Can we substitute t at this point? Which point are you actually referring to? Okay, I'm just continuing then. Okay. So now let's start multivariate optimization. Okay. F dash of x. Yes. In f dash of x, we are going to substitute uh, x equal to 2 because velocity is nothing but f dash, s dash of t. Okay. Yeah. So far, our goal is to find maximum or minimum values of functions of several variables, right? Of several variables. So now, in place of just one variable, so far we are looking at only x or t or something like that. We are looking at only one particular variable to solve. So now instead of one particular variable, if we are having more than one variables, then it is called as multivariate optimization. Okay, like we are optimizing many variables, not just one variable. Okay, so you already know the local maxima, local minima, critical points, right? So in this graph that in this image that you are seeing, which one do you think is the local minima? The local minima of this graph. X. Okay. Any other answers? Okay. So the local minima of this particular one is nothing but the origin. Okay. So x equal to 0 and y equal to 0. So this point is the local minima for it. Okay. Yeah. Yes, Kavya, you're right. 0 is the answer. Okay. Uh, yeah. So this one can be shown, as you can see, x is equal to x squared plus y square, which is nothing but the equation of a circle, right? So then we can tell, I mean, we can represent the plot, these values as a plot of the contours sets of this particular function x squared plus y square. Okay. And will also help us to understand the behavior of this function around its local minimum. So such a plot originally is shown here, as you can see. So here 1 and 2, these are nothing but the radius. Okay, so these are called contour levels, and you don't have to go much deep into it. Okay, right? So I just wanted to see if you guys still are with me. Can you just answer these two questions, question 1 and question 2? I want to know if the maxima or the minima of f of x exists when which of these three conditions are right. Is it A, B, or C? Yes, f dash of x is equal to 0. And if I'm looking at the maxima of f of x exists when, yeah, so f double dash is great, right? Okay. So, so these are for univariate. We are only focusing on one variable. That is what we have to follow. Okay. So if we are looking at multivariate optimization conditions, then what multivariate means we are having multiple variables now. So let us say I'm taking this particular thing. Z is equal to f of x1, x2 up till xn. Okay. Uh, so Z is equal to f of x1, x2 up till xn. And then similarly from the previously we are having the necessary condition and the sufficient conditions, right? So in the necessary conditions, we are taking f dash of x equal to 0. And in the sufficient conditions, we are taking f double dash of x is greater than 0 to get the mean, right? Okay. So for this necessary condition, for a multivariate problem, we are going to take the gradient of f x. So the x star here represents all the variables of x. Okay. So the gradient is nothing but partial differentiation of x with respect to each of the variables. Like starting from x1 up till xn, we are differentiating the function f with everything. So if I'm saying 2x1 plus 2x2, or let's say 3. Okay, if I'm saying this is f of x, if I want to differentiate f of x with respect to f of x1, then I'm going to take this as a constant. I'm going to consider that as a constant, and then I'll just write 2. Okay. In case if I'm taking the partial differentiation with respect to x2, then this 3, right? Yeah. So this is called as the gradient of the function f of x. Okay, so then we are going to write it in a single column vector. So that is the necessary condition. Okay, if we have to look at the sufficient condition is called Hessian. So, so initially how we are having gradient, here we are having Hessian. Hessian is nothing but the double partial differentiation of in all, not all. Okay, so it's basically like in a matrix, how do we write? 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, and so on, right? Similarly, here also you are going to do double differentiation, not single differentiation. Dou of x f by dou of x1 into dou of x1, which is nothing but dou of x1 square, dou of dou square of x f by x1 and x2 with respect to this, if you can see. Okay, x1 and x2, and then x1 and x3. And then so forth and so forth, you will continue a complete matrix. This is called as a Hessian. Okay. So the necessary condition is that the gradient have to be equal to 0. And the sufficient condition is that this Hessian matrix should be a positive definite, which means the matrix should have positive eigenvalues. Okay. If you're not clear about eigenvalues, you have to go back to week 2, I guess. Week 2 material again. You can refer to it. And if you need R code, it is available in week 2 folder. Okay. So guys, try. You want to try this one, or shall I do it? Option A is you do it. Option B is I will do it. Am I audible? Okay. So gradient of xf we are finding. So gradient of f we are finding, which is nothing but, since we are having only two variables, I'm taking differentiation of xf with respect to x1 and then differentiation of x with respect to x2. Right? We'll do it individually if you want it to be clear. Right? So in this one, we are going to treat x2 as a constant. Right? So a differentiation of a constant is always equal to 0. Here we are having x1. So differentiation of x1 is nothing but 1 plus differentiation of a constant is 0 plus differentiation of 4x1 square is 8x1 minus differentiation of x1, x2 is x2, and then it's 0 again. So it's like 8x1 minus x2 plus 1, right? And then differentiation of f, partial differentiation of x with respect to x2 is equal to 0 plus 2 plus 0 minus x2 minus 4x2. Oh, sorry, x1. So which is equal to minus x1 plus 4x2 plus 2. Right? Let me put this and this at the top. 8x1 minus x2 plus 1 minus x1 plus 4x2 plus 2. So far clear? Okay. So this should be equal to 0. So I'm equating both of them to 0. And 8x1 minus x2 plus 1 is equal to 0. Minus x1 plus 4x2 plus 2 is equal to 0. You can solve for x1 and x2 values. Okay. Uh, do you guys want to do x1 and x2 values? Okay. So you can solve for x1 and x2 and you will get x1 is equal to, let me just see what are the values. Okay. So x1 is equal to minus 0.19 and x2 is equal to minus 0.54. Yeah. Thank you, Kavya. Yeah. So these are the values. Okay. So that part is done. The first order necessary condition, which is gradient of x is equal to 0, is done. We have got it. Then the question is that we need to see whether the minima exists or not. The first and the second order as well. Okay. So the second order is nothing but the Hessian, which is two times difference. Sorry, two times differentiation of this, which is equal to d of f by d of x1 square, d of f by dou of x1, dou of x2. This one is also the same, dou of x by dou of x2 square. Okay, so you can solve for this and then you will get the values 8, minus 1 and 4. Okay, we are running out of time. We still have, ma'am, is this not? Okay. So once you get this matrix, what you have to do is you have to find the eigenvalues. So the condition is that the eigenvalues are positive. Okay. I have written it somewhere here. Yes. So the matrix should have positive eigenvalues. Hence, once we get this matrix, you have to find the eigenvalues. And if the eigenvalues are greater than 0, then the matrix is a positive definite, which means the minima exists at this critical points. These x1 and x2 values, these values. Okay. Is this notes available in NPTEL portal? Yes, this notes is it will be uploaded on Drive link. So a Drive link has been shared on NPTEL and from that you can access this as well as an R code. Okay. Okay. So I'll show you the R code for multivariate conditions. Okay, just give me a second. We hope it's visible. It's visible. Okay. So again, I'm taking a function, a random function here, right? So this function, I'm taking x and y as my two variables, okay? And f is equal to x square plus 5xy minus y square. Okay, so that is my function. Okay, let's run that. And then I'm trying to get the derivative with respect to x. So as I was telling it previously, we'll use the function d, and then we'll use the function, function variable f, comma, with what we want to differentiate it. So here I want to differentiate it with x, right? And I differentiate it and I get 2x plus 5y. Okay. So now let us try it for y. Then again, I'll print it for this y and I get this. Okay. So that is for gradient one, gradient one. So if I want to calculate the Hessian matrix, then I use this package called num-deriv. Okay, number deriv, num deriv. Okay, you can install this package. You can either write this line to install the package, or you can go to tools and you can install the packages. You just have to give this name. Okay. You can install that and then we can call that library. Okay. Again, I'm using a different function here. X1 square plus 4x2 square plus x1 x2. Okay. So this is an altogether a different function. To calculate the Hessian matrix, we have a function called as Hessian in this particular library, right? Then I give that and then I'll say which function it is and I'll give the shape of the matrix. Okay. So the Hessian matrix is stored in this variable with the name Hessian underscore matrix, right? And then I will print the matrix. So I got these values as my matrix, right? So that is all okay. Now I should see if the minima exists for it or not. So for that to happen, my eigenvalue should be greater than 0, right? So again, I'm using eigen function for that particular matrix. And then I got one positive, this one and this are my eigenvalues. And I have got both of them as positive. Okay. So yeah. So an minima exists for this. If you want, you can also give the equation that we have discussed in the previous problem here, and you can try it out as well. Okay. Can you give real-time industry implementation for multivariate, whether it's useful or not? Yeah, most certainly. Mm, so let us say in a factory, we are we are coming up with some product. Okay. So in that factory, we are taking multiple variables into consideration, be it the temperature, the material that we are using, like maybe the strength of the material, the temperature, the pressure, etc. and etc. So we want a point where we are using, like we want the production cost to be much more affordable, and we want to see where we can reduce the cost. So then in such cases, you can try things like you can reduce it. If I'm reducing the temperature, am I getting some reduce in the electricity bill? Okay, then is my production cost reducing? Or if I am using a different material, okay, a material of a different strength which is much more affordable, then is my production cost decreasing? So in most of the scenarios, you've taken multiple parameters into consideration to come up with something, and hence uh, that is where you use this multivariable optimization. Okay. Okay, I'll stop sharing this one. And again, we'll get back to some problem solving. Okay. So in a multivariate optimization, what is the critical point of a function? Again, in multivariate optimization, what is the critical point of a function? So a point where the function is undefined, or a point where the function has a local minima, a point where the gradient is 0, or a point where the function is linear. Which one do you think is right? So we have been doing it since long. Yeah, you guys are absolutely right. Uh, a point where the gradient is 0 is the right answer. So a critical point in multivariate optimization is a point where the gradient of the function is 0. So it can be a local minimum or a maximum or a saddle point. Okay. Uh, we'll see the next question. I'll just take it here. Mm. So in multivariate optimization, what is the role of the Hessian matrix? So Bayesian matrix is the matrix that we have discussed in the last page, the double differentiation of f of x in matrix. So what does it represent? It represents the gradient of the function, or it helps in finding the critical point, or it provides information about the function's curvature, or it is used to evaluate partial derivations. Yeah, you guys are right. So the Bayesian matrix contains second partial derivatives and provides information about the curvature of the function at a critical point. So this helps in determining its nature for us. So whether it is concave or convex, like is it like in a U shape, upward or downward, or things like that. Okay. Do you guys want to try this? Calculate the gradient for f of x comma y if f of x comma y and equal to 4x square minus 3xy plus 6y square at point 0 comma 1. Yeah, yeah, minus 3 and 12 are right answers. So, first we'll calculate the derivatives with respect. First we'll calculate the derivatives with respect to x and with respect to y, right? And then we'll put x equal to 0 and y is equal to 1 in that equation. And then we will get the values. Okay. So, but let's just see it again. Derivative of f of x with respect to x is equal to 8x minus 3y, right? And then derivative of f of x with respect to y is equal to minus 3x plus 12y, right? And then let's substitute x equal to 0 and y is equal to 1 here, and we'll get minus 3. In this also, we are going to do the same, and then we'll get 12, right? So minus 3 and 12 are the answers for this. You are absolutely right, guys. Okay, so shall we go to the next question? Yeah. So can you calculate the Bayesian matrix for this one? Bayesian is a double derivative with respect to x and y. The whole lecture later, yes, it will be available on YouTube. So the link and all is already there in NPTEL lecture. So once this is done, probably I will upload it on YouTube by tomorrow, and you can access the link through NPTEL portal itself. You will be able to watch it. Um, okay. Just wanted to ask, what is 6.39 and 13.6? We are supposed to get, okay, is it eigenvalues? I just need the Hessian matrix. Just the matrix is sufficient. Okay. 8 minus 3. Awesome. Amazing. Yes, that's a right, absolutely right answer. So, shall we try it out once again? So, we calculate differentiation, partial differentiation of f with respect to x, which is 8x. This is same. Yeah. Mm, just give me a second. I don't want to write it again. Okay. Yeah. Uh, so since we have this value, now we will calculate the double differentiation, right? Sorry. What do we get? We get x, 8, sorry. And then if we are differentiating it with x and y, then we will be getting minus 3, right? And if we are differentiating this with respect to y square, then we will get 12. Okay. Hmm. Since the Hessian matrix is nothing but f by dou of x1 square, dou of x by dou of x1, dou of y. Sorry, x and y. Dou of x by dou of x and dou of y. Dou of f by dou of y square, which is equal to 8 minus 3 and 12. Right? Okay. Next, we can try this question. Function f of x comma y is equal to x square plus 4y square, and it has a critical point at 2 comma 1. What is the value of function at this critical point? It is a really direct question. It should take like 10 to 15 seconds to figure out and do. What is the value of the function at this critical point? Okay. Uh, yeah. YouTube. Uh, this is directly uploaded in NPTEL. You can access it from there so that it will mark it as if you have watched it. So I would recommend you to open NPTEL, go for the problem solving session part. It will be at the end. If you go there, you will find the recordings part, and then the link will be there, and you will directly be redirected to YouTube. Okay. Okay. Um, Jairam is right. Answer is 8. Okay. We will. So here the catch is the critical points are already given to you. Okay. And I'm asking you the value of the function. Value is nothing but f of these critical points. So it's nothing but f of 2, comma 1. I'm sorry. Hmm. So which is 2 square plus 4 into 1, which is 4 plus 4 is equal to 8. It's a direct question. So just see when the critical point is already given, you don't have to calculate f dash of x and then again find the values. Values are already there, right? Okay. Um, so you can try this one. F of x is given, f of x comma y is given, and then I'm asking you what can be said about the critical point. So what I mean to ask is it a local maxima or a local minima or a saddle point or a global maximum or a global minimum? So what type of function critical points is it? Hint is that you can calculate the Hessian matrix and then you can find the eigenvalues. Based on that, you can give an assumption of what you're thinking. Is it local maxima or local minima, global maxima, global minima, or a saddle point? You can calculate the Hessian matrix first. Then based on that, you can tell what kind of critical function is at that particular critical point. So this is the last question for multivariate optimization problem. So okay, so it can be maxima. Okay, global maxima or local maxima? Minima, yes. Global or local? Same question for both of you. Global, okay. Okay. I'll tell that. So yeah, as usual, you will calculate the Hessian matrix. Okay, and I'm just writing it directly here. Okay, 6 minus 2 and 4, right? So once you get the Hessian matrix, what you have to do is you have to find the eigenvalues. Okay, so I'm just calculating the eigenvalues using R. So I directly have the values. So the eigenvalues are 5 plus or minus root 5, right? So now both of my eigenvalues are positive. Okay, both are positive. When I was telling the theory, maybe here. Oh, I'm so sorry. I did not mention it here. I'm so sorry for that. So eigenvalues are positive means the matrix is positive definite, which means it represents an existence of local minima. Okay, I'll write it down here. Eigenvalues are positive means okay. Please note this one. Okay, so if the eigenvalues are positive, it represents the existence of local minima. Okay, I'm so sorry for not mentioning it earlier. Uh, might have completely slipped my mind. Okay, so which means mm, it is local minima. Okay, okay. So next we are looking something else, unconstrained optimization problem. So it is basically like, imagine you are on top of a hill. Okay, kindly tell about global minima. No, in this particular multivariate problem, we only deal with local one only. Okay, we don't deal with global. Unconstrained optimization problem. Okay, so in this unconstrained optimization problem, imagine that a hill. Okay, on top of a mountain or something. You want to get to the lowest point possible. You think that there is a village at the least point possible, and you are trying to get to the bottom of that hill, right? So, as indicated here, first this human is going from here. He got down this slope like this. Again, at this point, he was searching for global minimum, local minima, and then he found the minimum to be here. So he went all the way till here, and then again he found that he can go down a bit. So he's doing some directional search. He is going in a way wherever he is thinking that there is a bottom point, he kept going. Okay, so this is called a directional search, right? So this one we have already seen, but in form of a 2D graph. We were seeing global maxima, global minima, local maxima, and local minima. But instead here we are seeing it in a 3D plot, right? So the maximum of all is the global maxima. And if I am looking at only what in between some points, then that is local maxima. And if I'm looking only at one particular point, then this is local minima. And if I'm looking overall, then this is my global minima. And if it is not maxima, not minima, it is somewhere in the middle, then it is called as a saddle point. Okay. So the our aim is to reach to the bottom point in the entire region. And the main thing that we see is the direction of the descent. So which side are we going? Are we going this side or are we going this side? So if I'm standing at this point, I can see that there is a direction this way and there is a direction this way as well. So which direction am I descending? that is also matters. And the steepest descent means wherever we are going, are we taking the steepest descent or not? Um, okay, let us just take this point here. Is it visible? Let us take this point here. Okay, so in case if I want to go down this way or this way, I'm seeing an angle. If this is my, if the angle of this is more, if it is more steeper, then I might prefer this rather than this. So we also look at this steepest descent, which is whichever one is possible. Okay. Sometimes we also have to climb to a point where we can see the least one. That means, let us say I have something like this. Okay. And I was here and then I went down. I can assume this as my global minimum, but still, who knows, if I go to this particular peak point and then see down, then I might find a much bottom point, right? So sometimes we also climb to the maximum, we also climb upward so that we can move downward. Okay. So the next one which we are going to deal with is gradient descent. So this is applicable to find the minima of the function. So for a given function f, we are going to find the minimum. And how exactly are we going to do? If you guys have worked on deep learning or things like that, you might have heard of back propagation algorithm to find some parameters. So this is usually the method that is used in back propagation algorithms as well. Okay, so you can just remember this one. So I'll explain this one by one. Okay, so if I'm having this function, if I'm having a graph like this, okay, and the starting point for me is x of k, xk, okay, and I want to go from this part to a different place here, so that this one, that can be my x of k plus 1. Okay, so how do I calculate if I'm going from this particular point to this particular point? That is given by this function here. This function here. Okay, so this alpha of k is nothing but the step size. So how much big step am I taking? Am I taking from here to here, or am I taking from here to here, or am I taking a step directly from here to here? All of that matters to me, right? So I want the step size to be taken, and also sk. Sk is nothing but the negative of the gradient of f. Negative gradient of f of the function. Okay. Um, try to remember that. So this gradient descent has a method to be followed. Okay. So in this method, the step one is iteration starts at xk. So if I'm going from here to here. So first I'm starting from here, and then I'll search which side is the steepest descent I have. So since this is my starting point, there is no other steep point for me. So I just want to go a step ahead. Okay. So I'm going from here to this point, and this new point is going to be x of k plus 1. Okay. So this x of k plus 1 tells me how much to move. Okay. So like that, I keep on going with respect to, and this continuous step keeps on rotating. So now this x of k plus 1 will become my x of k, and the new point is going to be my x of k plus 1. Okay, and this whole thing keeps going until and unless I find a point where which is the most is the minimum of the entire given function. Okay, let's look at a question. Okay, f of x is equal to x square minus 4x plus 1. Learning rate is 0.1. Learning rate is nothing but alpha. Okay, in deep learning for back propagation, we use learning rate. Okay, and the initial point is 9, which is x of k is 9. And this is the hint that I'm already giving. It's the same thing. X of k plus 1 is equal to x of k minus alpha times gra gradient of x of f. You guys want to try? Okay, so we are running short of time, so probably it's best if I do it. Okay. Okay. So we have f of x equal to x square minus 4x plus 1. Then we'll take the gradient f dash, just 2x minus 4, right? And then we can directly put it in this. X of k is nothing but 9 minus alpha is 0.1 into f dash is 2x minus 4, right? So 2 times x is nothing but this initial point again, which is 9 minus 4, which is equal to 9 minus 0.1 into 18 minus 4, 9 minus 0.1 into 14, which is equal to 9 minus 1.4, which is equal to 7.6, right? Yes, awesome. You also got it right. And so this is for one step. So I'm going from 9 to 7.6. Then again, this is my xk and this one is k plus 1. This is my first iteration. In my second iteration, I'll go from 7.6 to some other value. So then this becomes my x of k and this becomes my x of k plus 1, right? And then the iteration keeps on continuing until and unless I get to a point where I'm getting the least value there. Okay. Okay. So this is all okay. Now I'm having like various points, right? Let us say I'm keeping my initial point as constant. I'm taking the same quadratic equation, but I'm changing my learning rate. What happens when we are changing the learning rate? Okay. The learning rate here is so is very small. It's 0.1, and I'm able to go point by point, point by point, point by point. I was able to go, right? Oh, sorry. From here it goes down. From here I'm going down and down and down. At this point, you can see everything is so clustered up together because we are reaching almost the closing the minimum point. And at one point we came and we found the minimum, right? If we are taking 0.3, which is a bit higher than the previous one, then you can see the step size is too big. Here, the step size is only this much. From here to here, it's going. But from here to here, it is having a drastic change in a single shot. And then it is going faster and closer to the minima compared to 0.1, right? And then I'm using learning rate as 0.8. Then what happens is suddenly it has taken a turn from here to here, and then again it. So based on this learning rate, you keep on giving these values in that equation, and it keeps on moving and moving and moving, and finally you'll get to minima. At all cases, you are going to find the minimum. But how fast are you getting to the minima? In how many number of steps are you getting close to the minima is the main thing here, right? So having an optimal learning rate is very much important in any kind of a function. Okay. So now I'll show an R code. Okay, I'll try to finish it off fast. We are running out of time. Okay. Uh, I thought of explaining the entire algorithm here, but then it's the same. So if you go through this, you will understand. So basically, I am giving the same x of k plus 1 equal to x of k minus alpha and alpha times the gradient of f function here. The same thing I have written as a same formula I have written as a function. Okay, you can run it, and if you are not able to understand, then you can ask that to me in the next class. Okay, in the beginning itself you can ask. Okay, so this gradient descent, I have added that function to this variable called as gradient descent plot, right? I'm taking a function x square, okay? And then, okay, this is actually unnecessary. You can directly take the derivative f of f dash of x. And here I'm getting 2x. Okay, and I'm giving the parameters learning rate as 0.01, and I'm giving an initial x value as 100, and then the number of steps also I am giving as 500. Okay, and now I want to run the algorithm. So the algorithm is already saved in gradient descent plot, and I have to give the inputs of the function, the what is the learning rate, and what is the initial value of x, and the number of steps, right? So the trajectory, it is stored in trajectory. And now I want to visualize it. For visualization, I use this ggplot2 library. Okay. And then I'm storing all that data in this function df, in that variable df. And then I'm giving the plot. Plot should come here. I hope you can see. Right. So this is a plot that we can see when the learning rate is this much. Okay. So let us say I'm drastically changing it to 0.9 at once. Then I'm running the same things over again. And this is how the graph is entirely changing. So as you keep changing the learning rate, the graph also keeps on changing. And at one point it diverges into the minima. If I'm saying 0.5, then it will be a bit better than this, but still. Hmm. It has immediately reached the local minima at 0.5. Okay, let's give 0.1, and then you can plot it again. So you can try this out. You can try changing all the you can maybe like give 10 or 10 different learning rates, and then you can plot all the plots. You can all plot all the graphs together, and you can compare all of them. So that is something that you can do. Okay. Okay, so let's get back to this one. Um, yeah, you can try this question. X1 square minus 2x1 x2 plus 2x2 square plus 2x1. So you can also try. I think it's better if I just write the answers and one thing. Find the gradient of f. Okay. And then you can take x of k is equal to 0, comma 0 and alpha is equal to 0.5, right? Then x of x1 is equal to f of 0 minus alpha times gradient of f, and then you will get some value, and that value is going to be this. Calculate it, and x2 is equal to x1 minus alpha times of this, and then you will get, okay, calculate and you will get these values. Okay. Uh, I just want to go two more are left. I mean, two more sheets are left, so we can finish it off fast. Yeah, we have two variables in this one. No. So initially we were just taking the differentiation with respect to one, right? So when we are having two variables, you can take the Gaussian. I'm sorry, not Gaussian. That matrix that we usually follow. Before the Hessian, we were following gradient, right? This partial differentiation with respect to x1, partial differentiation with respect to x2. Same way you can do here, and you will get. Okay. Yeah. So we'll go for certain questions. And what is the primary goal of the gradient descent algorithm? Uh, to find global minima or to find critical points of the function, to find local maxima of a function, or to find the inflection points of a function. So the definition of global gradient descent itself is to find the local minima or the global minima, right? So gradient descent is used to find the minimum of a function. Okay. In the gradient descent algorithm, what is the gradient? In the gradient descent algorithm, what is the gradient? Is it a scalar value, or is it a steepest ascent, or is it a steepest descent, or a second derivative? So correct answer is C. It's the steepest descent that we are following. We are not taking the double differentiation. We are just taking one differentiation in that formula, right? That x of k plus 1 is equal to x of k minus alpha times this gradient of f, right? So this gradient of f is nothing but the descent, right? The negative value here indicates the descent of it. Okay. What happens if the learning rate in gradient descent is too small? Okay, so the gradient, um, yes, you guys are absolutely right. So a small learning rate causes the algorithm to take smaller steps in each iteration, leading to a very slow convergence, and it takes a lot of time to reach the minimum. Okay, so it converges slowly. Okay. Next, what is the relationship between the learning rate and the risk of overshooting the minimum? So here, if you want to know what overshooting is, so if this is from, if at all, I'm jumping from this point to this point, but my local minima is here, then I'm overshooting, I'm missing that, and I'm going to another part of the graph completely. So when does this happen? When does this like shifting of these parts happen? Yes, exactly. So a higher learning rate can cause the algorithm to take larger steps, which increases the risk of overshooting the minimum and oscillations around it. So it keeps oscillating here, there, and everywhere. Okay, that is do that. Yes, are absolutely right. Three more questions and we will be done. Okay, just bear with me for a minute or two. What is the disadvantage of using SGD? Okay, I haven't covered this. Okay, since I haven't covered this, you don't have to answer this one, but rather you can answer this, or you can calculate it by yourself as well. It's the same formula. Or there is another way also to get the value. Since we are already having this function and we are having the learning rate, and we just wanted to know the upgraded gradient descent, right? What you can do is you can multiply the learning rate with this x of k. I mean, not x of k, x comma y. Okay, so it is nothing but minus 2 comma 3 multiplied with 0.1, which is minus 0.2 comma 0.3. Okay, so the updated step is calculated uh, by multiplying it with the learning rate. Okay, then the last question. If the initial parameter value is 8 and the gradient descent is 0.2, what is the updated parameter value after one iteration? The gradient descent step directly is given as 0.2. So, which means alpha times gradient of f is equal to 0.2 here. Okay, and x of k is equal to 8. So, x of k plus 1 is equal to x of k minus alpha times of this, which is equal to 8 minus 0.2, which is equal to 7.8. Okay. And 3. Okay. Okay. That's all for today, guys. Thank you so much for joining. And this YouTube video, the recording of this will be uploaded on YouTube, and that link will be available in NPTEL portal itself. Okay. And then, yeah, this notes will also be uploaded in the drive. In the same drive, you can also have a look at the R code itself also. Okay. Yeah. So if you have no doubts, you can leave. I will continue with the rest of the doubts here. Okay. Thank you. Lavanya, I'll answer your question. Just give me 2 minutes.